this lab, we will learn to identify the dyes certified by the FDA for use in food, drugs, and cosmetics by studying the molecular surfaces of the dye molecules and how they influence their properties. We will examine each of the dyes' relative solubility or affinity for a different solvent. We will use the data from the introductory activity to design an experiment so we can identify a solvent that will give the maximum resolution of the mixture of dyes. We can further investigate the effect of the solvent concentration on the separation of food dyes. The results may be applied to study the concentration between structure and mobility of the food dyes.
So in this lab, we're going to start with a mixture of 3 different dyes. These are the dyes that are in the mixture, and our aim is to separate them all out. In the intro, we are going to use 2 different solutions, and we're going to see which one helps the dyes separate better. Then we're going to take that one and test the effect of different concentrations in the laboratory activity. Our different concentrations will be 0.5, 2, and 8%. You will choose one of these solutions after you test both, and you will see that the dyes have more affinity for one of them. You will explore the structure of the dyes and the solutions and see why.
So on the chromatography strip, make sure you fold the top 20 meters from the top, and then make sure you draw a line 15 millimeters from the bottom. And then you will put a dot in the center of the line, and this dot is known as the origin. And this is where you will put the entire mixture of the dyes, and it's where the dyes will separate.
Okay, so basically what we're going to do is we're going to put the chromatography strip into the Erlenmeyer flask, and we keep the flap over the edge. So basically notice we're not getting the solvent anywhere above the tip of our dye sample, because if we did, then the samples will dilute into the solvent. As you can see, on one of the chromatography strips, the dye traveled further and separated out more. So now it is up to you to eliminate one and take the other one and test the effects of different concentration on the dye. In the second part of this activity, we will be testing the effect of different concentrations of solute on the way that our dye will run. So we have a 0.5% solution here. Here we have a 2% solution.
And here we have an 8% solution.
So here's a sample of what your 3 chromatography strips might look like after you test the effects of different concentrations on your 3 dyes. RF stands for retention factor, and it is calculated by measuring the distance from the origin to the solvent front, which is the leading edge of the solvent as it moves through the paper. And you take the distance from the origin to each region of dye divided by the distance from the origin to the solvent front. Okay, so we measured our distance from the origin to the solvent front, which is all of this, and we got 8.6 centimeters. So for our RF value, we're going to measure the distance from the origin to each concentrated region of food dye. Okay, so let's say that the distance from the origin to the red was A, origin to yellow was B, and origin to blue was C. All you would do would be to take A divided by D, which is the origin to the solvent front distance, and this is all in centimeters, B divided by D, and C divided by D, and those would be your RF values for each food color.
So after you finish this lab, look at these 3 structures here that are started of the food dyes to help you understand why the dyes traveled and behaved the way they did. Keep in mind these interactions listed here, and when analyzing the structures, compare the intermolecular forces between the dyes, solutions, and the paper. A helpful hint is the paper is made of cellulose, which is a bunch of glucose rings. Different functional groups determine the different intermolecular forces and determine whether they stick to the paper or to the solution.